Hello, welcome to the REST Dispatchable Unit webinar. We are going to talk about REST Dispatchable Unit configuration. We'll start with the introduction, followed by the REST Dispatchable Unit configuration, use cases, results, and we'll finish with the web viewer and real monitoring. REST Dispatchable Unit has been developed for providing power production profiles, supporting on this way the operation of a hybrid power plants composed by variable PV and wind farm, non-variable RES, biomass and biogas power plants, and storage units, batteries and hydro pump storage, for different strategies according to following different use cases: to supply the power according to different power demand curves, to increment the revenues of the hybrid power plant due to energy sale, to demonstrate the capacity of hybrid power plants to provide ancillary services, and to demonstrate the functionalities of hybrid power plants after a zero voltage event. Besides to support different use cases, the main objective of this tool is to maximize the renewable energy penetration in the system energy mix, while the stability and firmness of the grid is warranted. Depending on the use case under consideration, the manager energy for hybrid plants inputs are different. These inputs are weather forecast, energy price forecast, power demand forecast, and system operator restrictions. This figure shows the schema of the REST Dispatchable Unit considering its inputs and outputs. Making use of the REST Dispatchable Unit configurator, it's possible to parameterize the main variables of each technology. In case of the photovoltaic model, the main values that can be edited by the user are the PV module characteristics, the inverter efficiency, the slope and azimuth of the model, the tracking system fixed or one axis. Also note that for each technology, there are 3 additional buttons: reset parameters to restore to default parameters, import parameters to import data from an Excel, save parameters to save an Excel with the current parameters of that technology. For the wind model, the main variables that may be set up by the user are number of wind turbine generators and its nominal power, height of the hub, wind turbine power curve. The hydro pump system configurator allows to set the nominal power, pump and turbine, the maximum and minimum capacity of the reservoir, the initial volume of the reservoir, the generator active power increase and decrease ramp rate. The battery configurator lets to change key parameters of the storage system, such as nominal power and capacity in hours, degradation rate per cycle, initial state of charge, charge and discharge efficiency. For dispatchable technologies, as the biomass and the biogas in next slide, the main parameters that may be configured by the user are the nominal capacity and the startup curves, cold, medium, or hot startup. In addition, for the biomass technology, the combustion efficiency of the boiler can be established. The high penetration of non-dispatchable renewable plants with an availability which is difficult to be predicted increases the need to balance the generation of demand and thus the need for ancillary services. In this respect, this use case aims to demonstrate the capacity of hybrid power plants to combine renewable technologies in order to provide frequency regulation when it's requested. Current markets are designed according to conventional generation plants, not considering the participation of renewable technologies or storage systems, for example batteries, in the procurement of these services. Despite the lack of actual regulation to provide ancillary services with RES plants, the manager energy for hybrid plants tool includes a flexible algorithm to modify and readapt the power production profile of its plant technologies, in order for them to meet with the power up and down commands that may come from the system operator. At this point, it's important to highlight that the power production profiles are recalculated without interfering with the production schedule which was agreed the day before. Battery management to provide us the battery installed in the hybrid power plants is used to provide two different services: load shifting, moving energy from periods with curtailment to others when the demand is not satisfied. The discharge commands for the day D are agreed calculated during the day before D1, and two, backup for provision of ancillary services. Charging and discharging energy according to the ancillary services order from the grid operator. These profiles must be calculated in real time during the day D. Since these two services can occur at the same time, the user must decide in the day D, in the day 1, what percentage of the battery is used for load shifting and what percentage will be allocated of or reserved to provide ancillary services along the day D. In any case, the three following operational restrictions must be ensured. 1. The sum of the power used to discharge at a certain time t cannot exceed the nominal power of the battery. 2. The energy stored in the battery, as a sum of the normal operation and the ancillary services provision, cannot exceed the total capacity of the battery. 3. The battery cannot charge and discharge at the same moment. Considering these limitations, the algorithm divides the existing battery into two subsystems: one battery model for load shifting operation and another which is used as a backup to provide ancillary services. This partition is realized by distributing the capacity of the battery in two parts. Finally, the battery initial state of charge shall be considered. More specifically, the algorithm has been programmed to allocate as much energy as possible into the partition of the battery aimed to provide ancillary services. Figure left shows an example where the algorithm does employ all the stored energy at the beginning of the day, although this energy could have been used in the moment to cover the demand, instead of using the gas turbine. Nevertheless, this energy is stored to provide ancillary services during the day ahead. This use case aims to demonstrate the hybrid power plant's profitability and its potential to increase the revenues when it's properly operated, in cooperation with isolated and non-dispatchable renewable technologies as PV or wind. For this purpose, the hybrid power plant will demonstrate its capacity to sell energy when the electricity price is high and store it when the price is low, employing the dispatchable RES for supporting both non-dispatchable RES and storage technology. Furthermore, this capability of the hybrid power plants will be useful for increasing the power stability and security of the system, allowing a reduction in the energy costs by avoiding deployment of old and inefficient technologies during the peak power demand. To test the functionality of this use case, a representative day has been selected with a potential difference among the energy prices during the day. Using this algorithm, it's expected a solution in which the production profile optimizes the reserves stored in the battery and in the HPS, which will be discharged only during peak hours. The hybrid power plant configuration selected for this demonstration is the same than in previous use case, but without biomass and biogas assets. The following two figures, figure left and figure right, indicate the results for applying this algorithm in comparison with the default strategy of injecting the stored energy as soon as possible after storing potential curtailment. The purpose of the restoration service is to restore the power supply in case a disturbance on national or regional level appears. It's based on the ability of certain generators groups to start without any external power supply after a zero voltage in the installations. These singular groups, like the hydraulic plants, can keep generating power in a stable way during the process of service restoration, acting as the auxiliary equipment that can be used to supply voltage and power after disruption. The resultant plans establish the coordinated process of all subjects involved in the management of the electricity system in the case of a national or zonal incident in the electrical system. Figure left indicates how the generation profile of the plant changed after a blackout. In this example, the failure occurs at 6:50 a.m. when the battery energy storage system was charged with part of the energy produced by non-dispatchable energies and when the hybrid power plant was discharging part of its initial reserves to cover the demand that could not be covered by the PV and wind assets. It can be observed that the agreed production schedule is terminated once the failure in the system occurs. Next, the battery energy storage system automatically tries to charge with energy production from the photovoltaic and wind plant and maximum charging power until it achieves its maximum capacity. The energy production that a battery energy storage system cannot absorb is called a curtailment. On the other hand, figure right shows the startup curve by each technology and how the hybrid plant could contribute to restore the electric system. This use case is focused on demonstrating the flexibility and the stability of a hybrid power plant in comparison with a typical conventional power plant, like the combined cycle, nuclear and carbon power plants, in terms of adapting the power generation to the power demand. Through this use case, it was demonstrated that the hybrid power plant concept is an alternative for the decarbonization objectives and the maximization of the RES penetration in the European power system. In order to test the functionalities of this use case, one representative day has been selected where originally the production of PV and wind exceeds the power demand during some hours of the day. The hybrid power plants considered for the analysis results is composed by the following technologies: PV, wind, battery, HPS, biomass turbine, and biogas turbine. After running this algorithm for the previously selected day, the results for a flat and a variable demand have been included in figure right and figure left respectively. As can be observed in figure left, the generation profile proposed. 1. When wind production is lower than the demand profile, all the wind production is injected into the grid. 2. When PV and wind production exceeds the demand, for example from 6 a.m. to 4 p.m. The curtailment stripe is stored in the battery, stripe green, or the HPS, stripe blue. 3. When PV and wind production cannot cover the demand, it's asked to discharge the storage units. 4. Finally, when there is not stored energy and PV and wind production cannot cover the demand, the dispatchable units, biogas and biomass, are required to produce energy. In order to investigate the impact of rest dispatchable unit of transient and frequency system stability, dynamic equivalent model of the whole rest dispatchable unit is developed. The use of equivalent dynamic model instead of the detailed dynamic rest dispatchable unit representation in system stability assessments eliminates the issue of high computational time required for conducting large system dynamic studies and availability of detailed information about rest dispatchable unit assets. The diagram illustrates the connection between dynamic equivalent model and manager energy for hybrid plants optimization algorithm. The output of manager energy for hybrid plants algorithm, for example, the production of individual system in the rest dispatchable unit, and chosen system stability study enabled the selection of the adequate equivalent model from the library of models. Equivalent dynamic model is connected to the transmission network at the point of common coupling. Methodology for dynamic equivalent modeling is based on identifying patterns in rest dynamic unit dynamic behavior using multi-year historical production data of individual plants in the rest dispatchable unit and artificial intelligence methods. Separate models are derived for transient and frequency stability analysis. Also, several equivalent model might be required to represent the rest responsible unit in a particular system stability study, meaning each model is suitable for a range of rest responsible unit operating points. A three-phase fault data transmission network bus is used as a system disturbance in delivering equivalent dynamic model for transient stability studies, as three-phase faults usually cause the most severe operating conditions in the network. On the other hand, an increase in total transmission network demand represents a system disturbance for frequency stability analysis. Dynamic equivalents are derived in the form of two transfer functions with voltage and the point of common coupling as an input signal and active and reactive power response at the point of common coupling as transfer functions outputs. Transfer functions parameters are estimated through an iterative optimization procedure with the objective of maximizing the match between the detailed and equivalent dynamic model output. Equivalent model accuracy is evaluated by comparing active and reactive power response at the point of common coupling obtained using the detailed and equivalent dynamic plant model for a range of plant operating conditions. Two standard indicators, root mean squared error and normalized root mean squared error, are used for quantifying equivalent model accuracy. 8 factors in annual dynamic performance of the rest dispatchable unit at the point of common coupling are identified in the case of transient stability analysis. A dynamic equivalent model is developed for each of the groups of power response. The values of the indicator for equivalent model accuracy assessment are calculated for all simulated case studies and presented in the form of box plots. As it can be observed, the root mean square error and normal root mean square error indices are characterized by small values for all 8 equivalent models, which indicates high model accuracy. In the case of frequency stability study, 7 equivalent models are required for representing annual rest dispatchable unit dynamic performance. The second and third equivalent model correspond to the largest number of days during the year, each of them accounting for about 25% time of the year. These models are the most dominant models in each month, except during the period from April to July, when the fourth and sixth dynamic equivalents have considerable time duration as well. The web part is integrated as a subsection in REST CC product as the main page of a hybrid power plant. Real and planned power production profiles can be monitored simultaneously. This is all. If you need more information, you can visit our website at crossbow.eu, on Twitter, on our YouTube channel.